4 of B, D, and F, right, divided by some normalizing constant. P is equal to that, right? That's the probability. And let's say we wanted to compute the normalizing constant, right? All right, how's the level now? Okay. So, right, all right. So let's do it symbolically. So the first one that we're eliminating is C, right? And if you look at C, its neighbors in the factor graph are A and B, right? And so what that tells us is that, well, we look at all of the potentials that contain C, right? And so we'll sum out C from that, and we'll create a new potential, right? So on the first step, we're going to get a big table, right, which we'll call 1, right? And that's going to have A, B, and C as arguments. And then we're going to sum out C, and we'll get a table that has just A and B as arguments. And that's going to be our first message, right? And so that's the first step of variable elimination, right? And then what happens, right, is we sort of scratch C off from the factor graph, and we have now, we add a new table, right, that joins A and B. Okay? And now we eliminate E, right? And so again, there's only one potential that has E in it, right? And so we have, you know, we put all of the potentials that contain E into one big table. That's just one of them. And so table 2 will have arguments B and E, right? Because that's this potential right here. And then when we sum out E, right, we'll get message 2, which has just B as an argument, right? And so we can cross E off of the factor graph and put another table now which has B as an argument. And now things start to get interesting, right? So we're going to eliminate A, right? And so table 3 is going to be all of the potentials that contain A, right? And so that will be phi 1 and, right, so not phi 1, right, but now we have a message which I'll call M1, right? So we have message 1, right? Phi 1 we got rid of by summing out C. We'll have phi 2, right? A, B, and D, we haven't summed out any of those variables yet. And then we also have message 2, right? So we'll call that M2, right? And so if we look at the union of all of those arguments, right? It's whoever's currently a neighbor of A in the Markov random field. So it's going to be, right? This is message 2. And so their arguments are going to be A, B, and D, right? And when we sum out A, we'll get message 3, right, which has as arguments B and D, right? And so if we hadn't already had an edge there, we would have added 1, right? And then the last thing that we need to look at is table 4, right, is all of the current arguments. We're eliminating B as the next one, and all of the current arguments, we've scratched off A, as B, D, and F. Right? And then at that point, it's all of the remaining variables in the factor graph, and so we can just sum them out directly from that table. Right? And so what I wanted to point out here is that you don't have to actually do the summing out and the creation of the new tables. You know just by looking at the structure of the Markov random field or the factor graph, and by looking at the elimination order, you know what tables you're going to create, and you know what messages you're going to send. Right? So does that make sense to everybody? That sound familiar from last time around? All right, that's good. So that's a list of the tables that we created. Something I wanted to point out is suppose that we stop variable elimination partway through, right? So let's say we eliminate just C, E, and A, right? So at that point, we've eliminated 3 things, right? We made the A, B, D, and now we've sent the message 3, right? So we have that. Our original, right, so if we go back to the previous slide, right, we had our original probability was the product of 4 factors, right? So we started off with phi 1 of A, B, C, phi 2 of A, B, D, phi 3 of B, E, and phi 4 of B, D, and F. And what we did was in the first step, right, we got rid of this table, and we multiplied in a new table, which I'll call message 1 of A and B, right? And then in the second step, we got rid of this table, and we put in message 2 of B, right? And in the third step, we got rid of this one, right? And we got rid of this one, and we got rid of that one, right? Those are all neighbors of B in the factor graph. And then we put in message, I need more space, right? So I'll put...
Isn't the third elimination A rather than B?
Did I do that wrong? You're right, so let's get rid of these. Right, so we got rid of phi 2 of A, B, and D. We got rid of M1 of A and B. We left M2 of B because we're not eliminating B yet. And we put in M3 of B and D, right? That's the message that we just sent at the end of that.
Could we get rid of phi 4 as well?
No, not at this step. Right, because we're eliminating A.
I just contradicted myself.
Yeah.
Sorry.
Right, and so now we're stopped after sending the third message, right? And we have 2 messages that are left, right? This M2, which has B as an argument, and M3, which has B and D as an argument, right? And one of the original potentials left, phi 4, because we haven't eliminated any of its arguments, right? And so what do we have now? Well, what we've done, right, is we've computed the sum over C of the sum over E of the sum over A of the product of phi 1, phi 2, phi 3, and phi 4, right? And we've shown that it is actually equal to this thing down here, right? This expression that we've created. Every time we do one of these summing out, we maintain basically the invariant that it's equal to the original expression with some of the variables summed out, and we sum out one more every time. So what does that mean? That means that if someone were to come and ask us for the marginal over the remaining nodes, right? So if somebody wanted to know what is the marginal probability of B, D, and F, right? Well, marginal probability of B, D, and F is exactly what you get if you sum out A, C, and E from the original distribution and then normalize to sum to 1, right? And so if we want that marginal probability distribution, it's actually equal to this expression that we just computed divided by a normalizing constant, right? So just let me say that again in words. At any given point in variable elimination, if you take the product of all of the remaining tables and messages, right? All of the remaining factors and messages, and normalize it, you get the marginal over all of the remaining variables, right? And so you can think of variable elimination as incrementally computing more like coarser and coarser marginals of your distribution, right? Eliminating one variable at a time until in the end you get the ultimate marginal, which is just the normalizing constant. Right? So that makes sense to everybody? All right. So before we get into using variable elimination some more, how expensive is it? Right? Well, it depends on the size of the biggest table that we create. In other words, it depends on the tree width of this graphical model under this elimination order. If somebody asks us in general how expensive is variable elimination, usually we'll say, well, it's the same as the tree width, which means the best exponential in the tree width, which means the best elimination order. But be warned that that's actually NP hard to find that one. And so maybe it would be more accurate to say it's exponential in the tree width of the best order we can find. And we can always hope to find the best order, right? And for a particular order, you can find the tree width without actually running variable elimination, right? We just did. We sort of simulated running variable elimination on that the very first slide, right? And the biggest table we constructed had 3 arguments, and so this graph has tree width 2. All right. So what you should know from these few slides and the end of last lecture, you should be able to understand the variable elimination algorithm for summing some nodes out of a factor graph. And you should know that it's possible to use variable elimination to compute marginals, conditionals, and so forth, right? And how to do that. You should know what a message is. It's one of the smaller tables we created during the course of variable elimination. And you should know what tree width is and why we care about it, right? It makes inference more expensive to have a big tree width. I also wanted to point out some gotchas, right? So there are a lot of things that you might if you use graphical models to work with your data and calculate probabilities, there are some things that are common problems that you run into. One of the biggest ones is data that's not IID, right? Independent identically distributed. So what does that mean, right? So if we're going to learn a graphical model, for example, we would hope to get IID samples of where each sample contains a measurement of all of the variables in our graphical model, right? That would be the simplest graphical model learning scenario. And if we get data but it's not IID, then learning is going to be trickier, might get you the wrong answer if you don't acknowledge that. In practice, we can tolerate some violations of IID-ness without problems, and we can't tolerate other ones, right? So you're not necessarily sunk if your data isn't IID. I guess I would say a rule of thumb is that if you're using the learned model to figure out what data you want to query about, that's when you're going to start getting in trouble. Basically, if there's a feedback loop where if you start making wrong predictions and then use those predictions to help you learn your model, then bad things can happen. Model mismatch, right? So we can make very complicated probability distributions with graphical models. And it's tempting to think that we've gotten, because we've made a very complicated probability distribution, and because the world is complicated, that we got the same one, right? But that's actually not usually true, right? Most of the time, when you write down a distribution using a graphical model, even if it's a pretty flexible one, the world doesn't respect your beautifully drawn out graphical model and gives you data from a distribution that isn't quite representable in that graphical model. Ways in which that typically happens, maybe the most common is an unmeasured covariate, right? So you'll have thought of 27 relevant variables, and the world knows of the 28th and 29th that you didn't put in your model. And so because those variables are relevant, they're going to mess with the distribution, right? Another one that's pretty common is that we'll assume some functional form for the conditional distributions or for the factors in a factor graph. So for example, it's pretty common to assume that You know, if a variable is real and more or less unimodal, well, then it must be Gaussian. And again, that's probably not true, although it might be close enough to true that it doesn't hurt us. The way in which Gaussian assumptions typically harm us most are the tails of the distribution, right? So in Gaussian distributions, the probability of very large deviations, it goes down as e to the minus x squared, right? If you look at the form of a normal distribution, that's really, really fast, right? It's exponential in the square of the distance from the center of the distribution. And so real-world distributions are often much more heavy-tailed, right? The probability goes down much more slowly. And so when this is true not just for graphical models, but anytime you're making a Gaussian assumption. If you make a Gaussian assumption and you predict probabilities from it, you're going to get the tail probabilities way too low. And there are probably going to be some outliers that mess with your estimation as well. And then finally, if you try to learn the structure of your graphical model from data, or if you have an expert come and tell you what the structure should be, probably either your learner or your expert will get it slightly wrong, right? And the more wrong that your structure is, the more your distribution is going to not match with the real world. And then I guess the last gotcha is, OK, exponential in tree width, right? That phrase should worry you. It's very easy to make runtime be very, very bad for graphical models. And so people often do approximations to try and make things run faster. But these approximations are another source of gotchas, right? Like you write down a beautiful graphical model. It's actually a really good distribution of the way the world is. But then you do approximate inference, and you get an answer that's nowhere close to the correct answer. Right? So yeah, so does that make sense? Are people have any questions about how to write down and do inference in graphical models? All right. Either that means nobody has any questions or everybody's totally confused. I hope it's the first. Although in reality, I suppose it's probably some combination. But let's go with heavy weight on everybody is happy with things. So let's take a look now to we'll try and make this a bit more concrete. And so hopefully that'll sort of make it easier to reason about these things that we've been doing in a very abstract sense so far. Make it concrete by looking at a particular example of a graphical model, which is a hidden Markov model. Probably a lot of you have heard of this one, right? But it's a graphical model in which you have some observed variables, x1 through xt, right? So you have a sequence of them. And then you have latent variables, s1, s2, s3, and s4. And the latent variables serve to explain the observed ones, and the latent ones are connected up in a chain, right? So you get a graphical model with the structure that I drew. So the latent state, right, so st will be discrete. So let's say an integer from 1 to k. Actually, let's say an integer from 1 to n. xt, the observation can be either discrete or continuous. We'll start with discrete observations because that's easier to think about. Let's say discrete 1 to k. The parameters of the hidden Markov model, right? You should all be able to read off from this what the parameters of the hidden Markov model are, right? Because a Bayes net tells you what parameters you need to specify it. Does anybody want to say what the parameters should be? Right. So what's the way to read off from a Bayes net, right? For every node, you need a conditional probability table of parents. I heard somebody say parents. Yes. So a conditional probability table of that node given its parents, right? So we can just go through all of these nodes, right? And so, for example, for an observation x2, what's the parameter we need? x2 given S2, that's right. So we need P of x2 given S2. And for a hidden Markov model, we're actually going to assume it's the same for every step, right? So this is called a time invariant hidden Markov model. So we'll have just P of xt given st, right? So that's one of the parameters. So how big is that parameter? Right? We have n discrete states and n discrete states and k discrete observations. So how big is that conditional probability table?
N times k?
Yeah, it's an n times k matrix. There's actually going to be only k minus 1 degrees of freedom in each row, right? Because the probabilities have to sum to 1. OK, how about S2, right? What are the parents of S2? S1, and so we need P of S2 given S1, right? And so in general, we're going to assume that that's the same for all t. And so it'll be probability distribution of, st plus 1 given st, right? And what are the dimensions of that? N squared, right? And are we done? There's one that everybody often forgets. What are we missing? S1, that's right. So P of S1 given its parents, which are none, right? And so that's going to be a vector in Rn, right? And again, you lose 1 degree of freedom because it has to sum to 1, right? So those are the parameters of a hidden Markov model. And then Bayesnet tells us how to write down the probability distribution, right? It's going to be, P of x1 to t and s1 to t is equal to, right? It'll be P of s1, P of s2 given s1, so forth, P of s3 given s2, times P of x1 given s1, P of x2 given s2, and so forth, right? So that's a hidden Markov model. And if we want to do inference in a hidden Markov model, right, what algorithm have we recently seen that might let us do inference in a hidden Markov model? The initials are V and E. Variable elimination. There we go. Right? So what does variable elimination look like? Right? So it turns out that if you apply variable elimination to hidden Markov models, you get some algorithms that were developed long before variable elimination was developed. So they have hidden Markov model specific names. So if we use variable elimination, let's say we want to try to get, suppose we want to try and answer the question, given x1 to, let's say the last one is x capital T, we want to find P of S capital T, right, the last state, right? So one way to do that would be to eliminate, let's eliminate all of the x's first, and then all of the states going from 1 up to t minus 1, so that we're left with just t, right? So what does that look like? Right, so we have at some, so when we eliminate one of the x's, right, what we're doing is we have, so let's eliminate xt, right? So xt appears only in one potential, right, which is P of xt given st, right? And so that potential is a k by n matrix. And so we've observed xt, right? And so what variable elimination tells us to do is to first instantiate all of our observed variables, right? So we get one row of the k by n matrix, right? And so that will be a length n vector, right? And that length n vector, it's right. The elements are how probable is the given observation for every state, right? So it's the vector of observation likelihoods, one per state. Okay. So that's the first step. Now, when we're eliminating some state, call it s little t, right? So if you look at the states, right, they have two neighbors, the state at the previous time step and the state at the next time step. And we get to state t. We've already eliminated state t minus 1, right? Because we're going from the beginning forward. And so we'll have a message along that we created, right? A message basically along the edge from st minus 1 to st, right? And so we'll get a message which I'll call alpha t, right? And its argument will be st, right? We had a table that had t minus 1 and t as arguments, and we summed out t minus 1. So we get a message that has st only as an argument. And that message is called the forward message, right? Or the forward table. We'll call at that time step. And then our goal is to compute alpha t plus 1, right? The message we send to the next hidden state, right? And so what are we going to do, right? So we'll have, we have alpha t, right? We also have, let's call this lt of st, right? The likelihood, the state likelihood vector. So what we'll have is we'll multiply together alpha t of st with lt of st, right? So these are messages from the previous state and from the observation. And then there's also a potential, right, which is the probability of st plus 1 given st, right? So we can multiply those together into a table which has st and st plus 1 as arguments. And then we sum out, right? We sum over st that, right? And that's equal to alpha t plus 1 of st plus 1. Right? And so that's the recursive step, right? We'll get in a message from the previous state. We'll get in a likelihood from our current observation. We'll multiply those together with a table with the transition probabilities, sum out our current state, and get a message to the next state, right? So does everybody understand that procedure? So the nice thing about hidden Markov models is that because they have a regular structure, right, we're doing the same thing over and over again. You can just write a big for loop that does all of this summing, right? You just go from state 1 on up to state t minus 1 to get the message to t, right? Now, one little implementation trick. There's a normalizing, so all of these probabilities in the discrete case are less than 1, right? And so we're multiplying together a bunch of numbers less than 1, and they're going to get smaller, right? And so if you just implement this naively in Matlab, after about 5-10 steps, you'll get underflow. Every message will be numerically 0, even though it's not actually 0, right? So do you remember from a homework, several homeworks ago, what to do in a case like that? That's right. So you keep track of a normalizing constant in log space. You just normalize the message to sum to 1, remember what you had to divide by, and keep the sum of logs of the normalizers, and you'll be good, right? And then actually in the end, if you're just interested in the posterior over S capital T, right, you're going to normalize it to sum to 1 anyway, and so that you can just throw away the normalizing constant instead of bothering to keep it. But if you're interested in the normalizing constant, right, if you want to know, for example, what was the probability of having observed the things that you observed, you'll need the normalizing constant to know that, and so you can keep track of it in log space. Okay. So, there's a very analogous process. Oh, I should say, before I go farther, in the forward case, right, the base case for the recursion is the message into S1, right? And that message is just the initial state probability. It's P of S1. So alpha 1 is just equal to P of S1, right? All right, so then the next thing is suppose now we want, now P of S1 given X1 to X capital T, right?
So alpha 1 of S1, is it just P1 of S1? Or
that's right.
P1 of S1 and L1 of S1?
No, the alpha, so you can adopt any convention you want as long as you're consistent about it. But the convention I'm adopting right now is that the alpha coming in does not include the likelihood of the current state. So the alpha is just the message that's coming from the previous state, and the previous state didn't know anything about the current observation. Right. All right, so the backward algorithm, creatively named to go with the forward algorithm, right? It's exactly variable elimination if you start with S big T, then T minus 1 all the way down to 2 to get the posterior over S1, right? I think that I am going to leave it as an exercise for the reader to actually do that, right? So this would be something interesting that you could work out on your own if you wanted to make sure that you have practice in working with variable elimination. The only thing I'll say is that typically they're called beta, right? So alpha for the forward algorithm and beta for the backward algorithm, right? And again, just like with alpha, you need to initialize beta. You need to normalize beta every so often and keep track of the normalizers in log space. And just like alpha, you need a base case for the recursion. Here, there's no, if you look at the last state, right, there's no potential that only the last state participates in. And so you can set beta capital T just to be uniform, the all ones vector, right? And then you multiply in the likelihood at time t, and then the transition probability matrix, and sum out st, and you're off to the races. Right?
Is this a prior?
Is
that a prior?
No. It's not a prior, right? You could make a graphical model where you put some kind of constraint on the end state, either a hard constraint or a soft constraint. That would not be an HMM. But if you had a constraint like that, right, a potential that only the last state participated in, that potential would become the initial value for the beta, right, beta coming into the last state. One way to think about it is, what is the absence of a potential? Well, it's the same as having a potential whose values are all 1, right? Because if you multiply everything by 1, you're not changing their relative magnitude. Right? So the all ones potential just represents the absence of a potential. Okay. You might have guessed, given a forward algorithm and a backward algorithm, there might be a forward-backward algorithm. Suppose now that we want the posterior over a state in the middle, right? S little t, where little t is between 1 and big T. Then you can run the forward algorithm up to state t, run the backward algorithm down to state t. They meet in the middle. You have a message coming from st minus 1, that's alpha t. You have a message coming from st plus 1, that's beta t. And you multiply together alpha t, beta t, and the observation likelihood at step t, right? And then you get the posterior at step t. So, let's think about what would happen if we wanted the posterior over all middle states, right? We could do this algorithm once for each middle state. Is that efficient? No. Right? You're wasting a lot of effort recomputing. The alpha t's are going to be the same no matter where you're planning to stop, right? You don't know where you're planning to stop when you compute alpha t, right? And so you just compute all of the alpha t's from 1 up to t. You compute all of the beta t's from t down to 1, right? And then you can get the posterior at every middle state, right, all at once. And so that's kind of cool, right? Instead of doing n runs of variable elimination, you're doing only 2, right? And so that's the key of the forward-backward algorithm. The thing that makes the forward-backward algorithm cool is that it saves you a factor of n over 2 work compared to separately computing the posterior over each state. Right? So what does this all look like? Let's see if I can show what this all looks like. Probably the technology will fail as soon as I unplug the little dongles, but we can always hope. All right. So, whoops. I have some Matlab code that I'm going to run here. So, OK, I've got a hidden Markov model now with, that's a relatively mild technology failure. All right, I have a hidden Markov model now with 100 states, right? And so I've put a transition matrix here where, if you can see, there's mass just above the diagonal, right? So this is 100 states connected in a circle, and you move forward a little bit on each step. And the amount that you move forward is slightly random because it's a fuzzy line instead of a hard line, right? So that's a transition matrix. I'm going to sample from the sequence of, sample some states from that transition matrix, right? And so each x here is a state, and you can see that they're sort of mostly just going up, right? Up in number, and then they wrap around to the bottom, and there is a little bit of randomness, right? And I can generate some observations, right? So that's a plot that you guys saw a couple of lectures ago, right? And I'm actually going to animate them, right? So here you go, right? You're getting noisy observations. It's going around in a circle, and you're getting noisy observations of where you are in a circle, right? So everybody understand what this HMM is doing? All right, cool. It's a little bit mesmerizing. I can run it again if you guys want to, experience the zen of it. All right, so, but let's suppose we didn't know the states that I used to generate it, right? So I can plot the observation likelihoods, right? So by the way, the noise distribution was Gaussian, so it's a continuous noise distribution. But the message from the state from the observation to the state is still the same. It's the probability of the given observation for every one of the possible states, right? So you can see, like, each column here is the state at a particular time step. And each row corresponds to a state index, right? So if I look, for example, here, right, at time 80 or so, the observation was such that all of the states around 40 were pretty probable, right? And because it was a pretty wide Gaussian distribution, this is a pretty noisy state estimate. You can see that it is in bands going up, but I have very little idea what the actual state is at any given time, right? So if I run the forward algorithm, right, I should get much nicer ideas of what the states are, right? You saw how the uncertainty went down, and now I have a much better idea what the state is at any given time step. I still have some uncertainty, right? You can see it's still a little bit blurry. And I can compare, if I want to the actual states, right? So I hope that's visible. I put an x for the true state, which I happen to know, on top of the heat map that tells me what the posterior probability was. And you can see that the posterior probability is doing a pretty good job, right? As you would expect, the posterior probability is, it contains the true state, right? Like the 95% confidence interval would contain the true state 95% of the time. So that's the forward algorithm. I can equally well do the backward algorithm. And you can see, right, so I'll go back and forth, right? There's after the forward pass, and there's after the backward pass, right? And it's slightly different, but approximately the same, because you're getting, instead of the information from past times, you're getting the information from future times here, right? So that's the backward pass. And then I can do now the true posterior marginals for each state, right? And so what I've done is I've multiplied the alphas and the betas together. Whoops, sorry. I've multiplied the alphas, there we go, the alphas and the betas together, and it looks like that. And you can see that compared to, for example, the backward pass, right, there's some uncertainty left. And if I look at the posterior marginal, right, I got rid of a bunch of that uncertainty, right? And that's because I'm using essentially twice as much information from the past as well as information from the future. And so I can compare that again to the actual states, and you can see that the actual states, again, the actual states are hidden, I don't know them, but for the most part they line up with my posterior over them. And if this were a better projector, you'd be able to see that even in the cases where they don't line up, there's still a little posterior probability there, right? It's not that it's zero posterior probability, it's just that it's indistinguishable from zero at the color resolution of a projector. Right? So hopefully this gives you much more intuition for what the forward-backward algorithm looks like. Right? Does anybody have questions on hidden Markov models? So I can post the code to do this. I'll post the Matlab code later today so that you can look at it. But this is maybe one of the best examples to start with if you're trying to get a good intuition for what variable elimination is going to do, right? Because you run it on a very regular graph, and you can look at the code, right, that does the calculations, and sort of it makes intuitive sense what it's doing. And you can check, right, that it actually gives you the right answer, which is always good. Usually in machine learning, we don't have the luxury of knowing what the right answer is. All right. So I'm going to tempt the gods of audiovisual equipment once again by switching back here. And all right. Woohoo. OK, so the forward-backward algorithm in a hidden Markov model, it's an example of something much more general. It's an example of something called belief propagation. And the idea behind belief propagation is that you can do, instead of doing variable elimination a whole bunch of times, you can do some pre-computation so that you can get the effect of having lots of different runs of variable elimination much more cheaply, right? And so in general, if you're given a factor graph or a Markov random field that's shaped like a tree, right? So if you go back to the hidden Markov model, that is definitely tree-shaped, right? There are no cycles in it. In general, a tree-shaped factor graph means that, a tree-shaped factor graph means that there are at most binary factors and there are no cycles, right? Binary mean two arguments connecting two variables. And actually, it's perfectly fine to have a forest instead of a tree, right? It doesn't have to be connected. But I'm going to assume a tree for now because you can just handle each connected component separately if you have a forest. what is BP going to do? It's going to simulate n runs of variable elimination for the price of 2, if you act now. What it's going to do is it's going to give you all messages that all n of those runs would have computed, right? And so those n runs, it's one run ending with each variable. And so that means you're going to be able to compute, for example, the marginal over any variable, the posterior marginal over any variable, right, from these messages. In fact, it turns out you're going to be able to read off the marginal over any subtree, right? Because well, why is that, right? If you run variable elimination and leave all of the variables in the subtree for last, right? We saw a few slides ago that you can get the marginal over that subtree by multiplying together all of the factors that are contained within that subtree with all of the message tables that come into that subtree from variable elimination, right? And so if you've got variable elimination runs, if you can simulate variable elimination runs in arbitrary order, then you can simulate one that comes in with all of the, leaves that subtree for last, and so you can get the marginal over that subtree. And so what that means is that it supports answering many queries very quickly, right? You do some amount of pre-computation, and then you just look up the answers to a lot of different queries. Right, and the time is proportional to the number of entries in, right, the time of belief propagation is proportional to the number of entries in the largest table. In other words, it's exponential in the tree width. And then the time of reading off the marginal is proportional to the size of that marginal, the number of entries in the table that you're going to compute. So the algorithm looks like this. Let's say that we have a factor graph that is a tree. So I'll draw a factor graph that's a tree, A, B, C, D, and E. Right? Actually, I'll draw it as a Markov random field. I won't bother to put the little square nodes in the middle of the binary factors. So the first thing we do is we pick a root, right? And we hold it up by the root and let it dangle down. So let's pick B as our root, right? And so we'll have C, D, and E, right? And A coming off of the other side of B, right? And we're going to run, the first thing we're going to do is run variable elimination inward to the root, right? So that means that we just repeatedly pick a leaf and eliminate it and send a message to its parent, right? So I'll eliminate, D sending a message to C, E to C, then C becomes a leaf at that point, so I can eliminate it and send a message to B, right? And then I can send a message from A to B, and now I'm done, right? Then I'm going to loop over all of the leaves, and I'm going to run variable elimination outward from the root to all of the leaves, right, to each leaf in turn. But the trick is that I'm going to reuse messages where possible. So for example, let's say that I want to run variable elimination ending at the leaf D, right? So, I'll start at the root B, right? And then I'll eliminate all children of the root other than the one that leads to D, right? And so I would get, to do that, I'd get a message coming from A to B. But I already have that message, right? I computed it already when I was doing variable elimination going upward towards the root. So I save that, right? Now I compute a message down from B to C by summing out B, right? Now again, I'm at C, and I'm going to eliminate all of the children of C other than D, right? And so I already have those messages. I have the message from E to C, and so I can then compute the message that goes from C down to D, right? And so then if I go over all of the leaves, right, now suppose I'm eliminating E. Well, it's even better, right? I already have the message from A to B, and I already have the message from B to C, because I computed that when I was going down to a different leaf, right? And so now the only message I need to compute is from C down to E, right? And then when I go to A, I need to compute a message down to A, right? And so at the end, what's going to wind up happening is that I'm going to compute 2 messages for every edge, one going up towards the root, and one going also up toward the roof if I point my tablet towards the roof, and one going down towards the leaves, right? and I never need to recompute a message, right? So it's worth, by the way, convincing yourself that it doesn't matter if I'm looking for a message from, let's say, C to B, right? It doesn't matter what order I eliminate the nodes in C's subtree, I'll get the same message, right? So there really are only two distinct messages that I can send over each edge. And the reason for that is basically that associativity and commutativity work, right? That you can, if you're summing out the variables underneath, you maintain equality every time you sum out a variable, and so it doesn't matter what order you do them in because of associativity and commutativity, right? So so that's belief propagation, right? And just to remind you, the reason we did this is that now I can compute the marginal over any subtree very easily, right? So for example, suppose I wanted to compute the marginal over C and D. Well, there are messages going into that subtree from E and B, right? And so I'll just take those messages together with any potentials that are local to the CD subtree, multiply them together and normalize, and I have my marginal. All right? So questions about belief propagation so far? All right. So an interesting point is that whenever I'm computing messages, I'm doing it very locally, right? So if I'm at a node B that has neighbors, let's say A, C, and D, right? And I want to compute the message to C, right? This message. What I need to do is I need to have the messages coming in from A and D, right? Together with any local factors that involve B and C, right? And I multiply together the messages and the local factors, sum out B, and that gets me my message to C, right? And so the general algorithm is if you want the message along any edge going outward from a node X, you get all of the incoming messages from all the other neighbors of X, the ones that are not along the edge that you're trying to send a message along. Those are going to be functions of X, the node in the middle. You multiply those messages with the factor that goes along that edge, right? So if the other node is Y, it'll be a factor of X and Y. And you sum out X to get a function of Y only, and that's your message. Okay. So for example, if all of those nodes are binary, if A, B, C, and D are binary, right, you'll have the message from A to B. That will be have B as an argument, and it will be a table with two elements, right? So it'll be, let's say, if B is true, it'll be 3, and if it's false, it'll be 4, right? And the same thing, we have the message from D to B. Again, that's going to have B as an argument, and let's say if B is true, it's going to be 1, and if it's false, it's going to be 6, right? And then you'll have the factor of B and C, right? And that's going to have two arguments, B and C, right? True, 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 false, false, true, false, false are the possible values, and that'll have some numbers in it, right? 1, 2, 2, 1, right? And so I multiply those all together, right? So let's actually do that, right? So this is B and C, right? So I'll multiply together these two messages first, right? I can combine them, and that becomes, for true, it becomes 3, and for false, it becomes 24, right? And then I can combine those two guys to get a table, right? It's got 4 elements, right? And when B is true, I multiply by 3, so that's going to be 3 and 6, and then 48 and 24, right? And then I sum out B, right? So I sum together 3 and 6 is 9, and I sum together 48 and 24, and I get 72, right? So I have a local algorithm for computing a message along any edge, right? And what belief propagation is doing is it's scheduling which edges I look at in what order, right? I do a pass of messages up from the leaves and then downward from the root, and I can just visit the nodes in any order downward from the root as long as I visit parents before children, and I can visit the nodes in any order upward from the leaves as long as I visit children before parents, right? So I'm doing something nice and local at every node, which is, good for, I don't know, keeps memory accesses local. It keeps the algorithm understandable, right? It's just nice to be able to think of it that way.
Sure, when you sum out B, shouldn't you just sum with 3?
You're right. I should. Thank you. So we'll erase the evidence there. And 3 and 48 together are 51, and 6 and 24 together are 30. Thank you. This is why we make a computer do it instead of doing it ourselves. Right? Once you get the code right, the computer is going to get it right every time. All right, so the next question is, what if I said how to do belief propagation for a tree? What if the graph isn't a tree, right? Most of the models that you see are probably not going to be trees. So the first answer is really, I don't know, almost a cop-out, right? Pretend it's a tree. Initialize all of the messages, so one message along each edge in each direction. Pick an edge in a direction and recompute the message according to that local algorithm that I just gave, right? Like look at all of the other incoming messages into the source node of that edge, right? And then I repeat. I pick another edge and direction and recompute its message, right? And I visit every edge in every direction multiple times. And if I'm lucky, this will converge. And that is the sum total of the theoretical analysis of loopy belief propagation, more or less. If I'm lucky, it will converge. That's a little too flip. People have spent a lot of effort trying to analyze loopy belief propagation, and they have some nice results. But the results are for special cases, or they depend on conditions you aren't going to be able to check. So really, what people do in practice, if they want to use loopy belief propagation, is they try it and see if it works, right? There is a nice bit of folklore, which is supported by a little bit of theoretical analysis, which says that if it happens to converge, it's probably getting you something pretty close to the right answer, right? Which is nice, because that way you know, like if you try loopy belief propagation and it seems to work, then it probably is working. Right. So the sort of thing that you can check, there's one easy to check thing which you can use to figure out whether loopy belief propagation is a good idea or not. And that's whether the potentials are what's called frustrated. So a frustrated potential is something like this, right? We have a loopy graph with nodes A, B, and C, right? And you have a constraint that says A is not equal to B. You have a constraint that says B is not equal to C. And you have a constraint that says C is not equal to A, right? Now, if those were hard constraints, there would be no satisfying assignment. But let's say, softly, right? Meaning that you have a potential which has a larger value if they're not equal and a smaller value if they are equal, right? So then, depending on how soft or hard this potential was, in other words, on what the ratio is between the case where they're not equal and the case where they're equal, the potential will be more or less frustrated, right? You have, basically, if you look at any two potentials, they give you an answer which disagrees with what the third potential wants to give. All right. And you can imagine the frustrated researchers coming up with the idea that their potentials are frustrated when their loopy belief propagation isn't converging. All right. The other thing that we can do, sorry, go back. Answer 2, right, is that we can build a different graphical model that is a tree, right? And there's an algorithm for doing that called the junction tree method, which we're going to cover in a little bit. And so as long as you can build another graphical model that encodes the same distribution but is a tree, then you can run belief propagation on that tree, and you're going to be good. Right? Now, of course, the problem is that when you try and construct the model, it might be that you make your graphical model a lot larger by trying to achieve that it's a tree. Right? And so this isn't always feasible. And so answer 3 is to do a combination of both. Right? You sort of push it a little bit towards being a tree, as much as you can afford to do, and then you run loopy belief propagation on that tree. Not tree, right? You pretend the not tree is a tree, but now because it's closer to being a tree, you hope that loopy belief propagation is going to work better. Right? And that works exactly as well as you might think it does, which is to say some of the time. Right? So the only guaranteed answer is the expensive one. You build the junction tree. But the non-guaranteed answer can work pretty well in practice. So how do you make something closer to a tree? You do it by grouping sets of variables, right? So if you have, let's say, a Markov random field that's like A, B, C, and D, right? So that has a cycle in it, so it's not a tree. You can group together the variables B and C into one variable, which I'm going to call BC, right? And so I'll get something that looks like this: A, B, C, and D, right? And what do I mean by grouping them together? I mean I create, so if B and C both have, let's say, 3 settings each, then BC has 9 settings, right? The product of the number of settings of each of the component ones. And I can come up with a distribution over BC, and I can marginalize it to get the distribution over B, and marginalize it the other way to get the distribution over C, right? And the same thing with factors, right? Any factor that involves B, I can turn it into a factor that involves BC, right? And any factor that involves C, I can also turn it into a factor that involves BC, right? And so I've got this bottom graphical model here that is a tree, and I got it by merging together 2 of the nodes in a non-tree, right? So again, we're doing this to make the graph more tree-like so that belief propagation is going to work better, either BP or loopy BP. So another interesting example, right, is so I could group B and C and get the one that I just showed. I could also group, let's say, A, B, and C together, and B, C, and D together, and get this tree, right? So I have now 2 overlapping groups of variables, right? And just as before, I can, every factor that was in the previous graph, I can turn it into a factor that, works on one or both of these nodes, right? The only thing that I have to do that's different is I have to have a hard factor that constrains the setting of this node, right, has to agree with the setting of that node on B and C. Right, so a setting for ABC, right, there's 8 possible settings for ABC. There's 8 possible settings for BCD, right? And I can't just pick an arbitrary setting for ABC and a different arbitrary setting for BCD, right? Because ABC tells me how B and C are set, and BCD also tells me how B and C are set. So I have to pick an assignment that agrees. And I can think of that as being a hard factor, a factor that gives me 0 probability if the 2 don't agree with one another. All right? So the junction tree method converts a factor graph into a tree by doing this sort of variable grouping. And so given an original factor graph, a junction tree is a graph that is a tree, hence the name. The nodes are going to be sets of variables from the original graph. So we've gotten the nodes in the junction tree by grouping sets of variables in the original graph. Every original factor in the original graph, we're going to group variables such that all of the arguments of that factor belong to the same node, right? There could be other nodes that contain those same variables because we could choose overlapping sets, but there's going to be one node that contains all of the arguments to each one of the individual factors. And then we're going to enforce something called the running intersection property that I'll get to in a slide or two. So the semantics of a junction tree, right? A junction tree is yet another type of graphical model. but its semantics are basically the same as a factor graph semantics, right? You have nodes and you have potentials on those nodes. The only difference is that implicitly there are also constraints that the assignments have to agree on nodes that contain the same variables, right? So there's these consistency constraints as well. And you can think of the junction tree method as basically following along with a run of variable elimination and watching the tables that we create, right? And grouping variables so that every time we create a table, it's going to be a subset of some node in the new model, right? So there's going to be a many-to-many correspondence of junction trees with elimination orders, right? So you can run variable elimination different ways and get the same junction tree. And there's going to be actually a little flexibility in variable elimination that lets us get different junction trees depending on how we run it. But the first thing that most graphical model software does when you ask it a query is to build a junction tree and pass messages in that junction tree so that it can then answer your queries faster from then on. All right, so we should, so let's see, the running intersection property, I promised to define that. So in variable elimination, right, we have a variable x, and once we start looking at tables that contain that variable x, right, we're going to have a table that contains x until we eliminate x from the model, right, until we sum it out. And then once we sum it out, then x isn't going to participate in any more tables, right? Because we summed it out of all of the tables that contain it. So what that is going to mean in a junction tree is that every node containing x, if you collect all of those nodes together, you get a connected region of the junction tree, right? And if that's true for every variable, right? If every variable's region of the junction tree is a connected component, then that's called the running intersection property. So why do we care about the running intersection property? Well, if you look on the previous slide, right, so I had 4 conditions for a junction tree. And those conditions turn out to be an if and only if. They're necessary and sufficient conditions for being able to represent the original graphical model as a junction tree, right? So if any of those isn't satisfied, then there's going to be some way of setting the conditional probability tables so that you can't represent the distribution in the putative thing that isn't the correct junction tree, right? And so that's why the running intersection property is interesting. It's a simple graphical test that makes that into a set of necessary and sufficient conditions for being able to represent a factor graph in a junction tree. All right. So let's build ourselves a junction tree. So we did this example right at the very first slide of class. I'm not going to do it again. I just have a list of all of the tables that we created. So what am I going to do? I'm going to create, for each of these big tables that I created, I'm going to make a node in my junction tree. So we have a node for a node for A, B, and C together, a node for B and E together, a node for A, B, and D together, and a node for B, D, and F, right? And now I'm going to connect them based on the messages, right? So I have a message AB coming out from this node, from the node up here, and that message, if you look in the progress of the variable elimination algorithm, eventually it's going to get multiplied into the ABD table, right? So I'll label an edge from ABC to ABD with the message A and B, right? And then the same thing, the BE factor, the BE table, there's going to be a message that's just on B that also gets multiplied into the ABD factor. And then when I eliminated the ABD table by summing out A, I created a message BD that connected eventually was going to be multiplied into the BDF table, right? So basically the summary is that you make a node for every table that you create in the variable elimination algorithm, and you connect up the tables according to where the messages go, right? So you have a message leaving a particular table after you sum out one of its variables. That message gets multiplied into another table, and you connect up the first table to the second table. And you can label it with the message if you want to. All right? So an interesting fact is that if you look at the labels of the edges, right? So for example, here if you look at this, then B is equal to the intersection of BE with ABD, right? And that's true on every edge. The message arguments are going to be the intersection of the nodes on either side, right? Just a bit of terminology, those message arguments are called separating sets or sepsets because they're on the edge that separates pairs of nodes. Okay. So just as a recap, inference with belief propagation, right? So what you do is first you build a junction tree, right? So I said last lecture how to do inference with variable elimination, right? And now I'm saying how to do inference with belief propagation. And the reason that we want to do belief propagation is that it's more efficient than variable elimination if we're answering lots of queries, right? So the way you do inference with belief propagation is first you build a junction tree. For example, you can do that by looking at the message tables for some elimination order. You can share that junction tree among multiple queries, so you build it once, right, and share it among a bunch of queries. Then every time you get a query, you instantiate the evidence, right? You pick a root for your junction tree, right? You can pick any node as root, and you pass messages first up and then down in the order that I described before, so that you get 2 messages on every edge, 1 in each direction. The arguments of those messages are called separating sets. Then you pick a subtree of your junction tree that contains the variables that you care about, the variables in the query. You read off the distribution of that subtree by multiplying together all of the messages into that subtree with all of the potentials that are local to that subtree. And then you sum out all of the nuisance variables, all of the variables that were in that subtree but that were not in your query. All right? Yes?
You said BP is more efficient than variable elimination, but you need this message to do BP, and for message you need variable elimination to get a message.
Right. So BP is as if you made many runs of variable elimination for the cost of 2. Right? So that's why I'm saying BP is only more efficient if you need multiple queries that you can answer using the same junction tree. Right? So for the first query, it's actually less efficient because you go through the overhead of building the junction tree. Right? But for the second query, you're starting to break even, and by the time you've done 10 queries with the same junction tree, then you've saved yourself a lot of time. That's a good question, right? More efficient is only true if you're doing many queries that you can amortize the junction tree over. So questions about inference with belief propagation? All right, so I want to mention, I've been talking about discrete variables only so far. Graphical models can have continuous variables too, right? You can have, for example, normal conditional probability distributions. So the changes you make are basically the ones that you'd expect. Every time you have a conditional probability table, it becomes a conditional probability density function, right? Every time you have a potential table, it becomes a potential function. Right? It can have a continuous argument instead of a discrete one. Messages as well become functions as opposed to tables. And every time you wanted to sum out a variable, right, if it's a continuous one, you integrate it out instead. Now, you should all realize, right, you should all be asking, how do you do all of these integrals, right? Typically, you can't do the integrals exactly, or it's really, really expensive to. So that for big discrete ones and definitely for continuous ones, it's really common to represent the messages approximately, right? So your message is supposed to be a table or a function whose arguments are all of the variables in a separating set, right? And so if some of those variables are continuous, you're going to be representing, let's say there are 3 continuous arguments, right? Then you're going to be representing a 3-dimensional function that's the message, right? And the function is interpreted as how likely are the different assignments, right? So it's like a probability distribution, except it doesn't have to be normalized. So any way that you can think of to approximately represent a probability distribution, people have tried for representing messages approximately. So for example, a mixture of Gaussians is a good way to represent one, or a sample, right? You just take 1,000 samples from your probability distribution and you represent the distribution with those samples, right? You can also do it with statistics, right? People will represent a distribution with its mean and variance and skew and kurtosis, right? And all of these moments. And so you can do the same thing for a message. And basically anything that you can think of to try for that, people probably have tried. And so I wanted to just close with a quick example of what inference looks like. So we're not going to be doing it formally, but I wanted to give you just the picture of what inference looks like in a continuous graphical model. There we go. All right, let's start again. So we have now imagine a robot with a single range sensor that's repeatedly observing the range to a fixed landmark. And it's repeatedly observing odometry that tells it that it's going forward at a fixed speed, right? So now the variables are the x, y, theta position of the robot, right? And so I can represent, that's a 3-dimensional probability distribution. I'll represent it with a set of samples from that distribution. And if I run a particular inference algorithm for approximating the messages, there we go, right? So as you expect, the robot is going around in a circle in order to be able to keep measuring the same distance from the landmark, right? Even though the odometry tells it it's probably going straight, it's getting curved into a circle, right? And this particular inference algorithm is called a particle filter. You may have heard of them. They're pretty useful. And if you want to learn more about Markov chain Monte Carlo inference in graphical models, you should probably take the graphical models course, because we're not going to have time to cover that in any detail here. So any questions about the continuous graphical model ending on a pretty picture slide? All right, then let's end on a pretty picture, and we'll see you guys on Monday.